Hey, and we're back. Did you miss me? Probably not, but that's okay. Let's go ahead and finish this problem. So we were left, here we are, it's A2 section 5.4. We were left thinking about this problem, how to factor it. Should we factor this way or that way? We said we are going to do both. So let's get started. We do have a couple more problems to do, but I needed to get rid of it so we could have some space. Let's go down our orange path. And so what our orange path is doing is looking at this as a difference of cubes. So the one thing we need to do is figure out what the rule is for difference of cubes. If we scroll back up, we would see that our rule is as follows. So we're going to use this model to think through how we're going to process this here. So we know when we have this, let me rewrite ours, our difference of cubes. When you have this, you're going to take the thing that's being cubed, in this case, m squared minus n squared, okay? And then inside, you're going to take that thing that's being cubed, m squared, and square it, m to the fourth power, plus those two things that are being cubed, m squared, n squared, plus that thing that's being cubed on the right. You're going to take that to the second power, so that's n to the fourth power. Okay, I know that looked crazy, but I hope you can see the logic in it as we process through this orange process, right? And so this is what we got. We thought about it this way, we got through here, and what I want to show you is that now we're at m squared minus n squared times a whole lot of stuff, right? This thing here. Now this thing, as it stands, for me, we don't have a factoring law that's going to work out. I've looked at our factoring laws. When I have a trinomial here of this form, it does not factor in a way, as far as I know, it doesn't factor in a way that is fruitful. But this part can factor because it's a difference of squares. So this tells me I can have m plus n times m minus n times all this stuff. I don't think this factors. But what I'm going to do is I told you we were going to look at it in two methods. Let's see, we're going to factor it, so it's going to be equivalent. Let's see what our equivalent value gives us when we think of it in terms of the purple. So coming over here, let me give myself a little bit more space. I'm looking at this as a difference of square off the bat. So I'm thinking about the rule a squared minus b squared equals a plus b times a minus b, and I'm going to apply it to our situation. When I do this application, what I end up with is m cubed plus n cubed, right? And then m cubed minus n cubed. You see that? So I do the a squared minus b squared is equal to a plus b, a minus b. This squared minus this squared is equal to this plus this, and times this minus this. You with me? All right, so hopefully that made sense. So highlighting my purple process over here, what I'm going to do is now look to see if I can break down the thing that I've gotten. I can, right? Because here is legitimately a sum of cubes, and this is a difference of cubes. And are we going to get the same thing? That's what I'm wondering. So let's see what happens. The sum of cubes law, which looks like this, the sum of cubes law for factoring, or factoring breakdown, looks like this. And that means that I can write m cubed plus n cubed as this. Okay, so I've taken this, only this part, and I factored it out to this. And now I'm going to do the same thing over here. And the first thing I do is recall the law for the difference of cubes, and then I apply and I get this situation. So here's the breakdown of my difference of cubes, the breakdown of my sum of cubes in my problem. And look at this. I get m plus n in my purple method, right? I get m plus n times m squared minus mn plus n squared times m minus n, and then times this here. And notice that these are very similar, but the thing is, and I'm going to use a red pen to show you, the thing is, this part is broken down into this and this. What I'm saying is, I don't have a technique for factoring a trinomial into two other trinomials. I don't really know that one. So It does matter when you start a problem how you perceive it to know whether you're going to be able to break it down as much as possible. The purple method is superior because this is more completely factored. Whereas this method here, we would have gotten stuck with something that was not factorable according to our laws, because none of our laws, if you come back, none of our laws give us an opportunity to take a trinomial and break it down so that it's the product of two other trinomials, right? Every time we do it, it's like a binomial. So here, I just want you to observe that choosing the purple path, I know I'm talking a lot. Just bear with me for a minute. Choosing this purple path is the way to break it down completely. So if you're like checking your answers in the back of the book, or you're looking, you're like, why did the text get this? Or why did I get a different answer than you? Perhaps it's the way we started off the factoring. So I want you to keep that in mind as you proceed. So now we got some other examples. This was fun, but let's move on. So in this example, what we're working on in example 4 is the quotient of two trinomials. So we're looking at simplifying this situation. And so one thing that you want to do anytime you have a situation like this, the best way to handle it is to factor first and see if you get common factors. The analogy is having a number like, I don't know, let's say 144 over, I don't know why I chose that number, over let's say 256. And I say, okay, can you simplify this? You know from your experience with fractions that you would want to see if there's a common factor, right? A greatest common factor out of these and break it down. One other way of thinking about this is to prime factorize it. Make the top as factor it down to its prime values. So I know 144 is really 12 times 12, right? And then I know 12 times 12 is 3 times 4 times 3 times 4. Stay with me. I know this seems a little crazy. And basically, 3 times 4 times 3 times 4 is really 3 times 2 times 2. And then another 3 times 2 times 2. So the prime factorization of 144 would be 2, because I got 4 of those, 2 to the fourth power times 3 to the second power. Usually we do this with factor trees. I'm going to do the same thing down here with the 256. Well, 256 is kind of interesting because I think this is a whole lot of 2's being multiplied together if my memory serves correctly. So when I break this down, let me go factor tree route this time. Let's say this thing could be, I don't know, 4 times, 4 goes into that, 6 times with the remainder of 1, 4 and 62. Okay, so I get 4 times 64. Break this down as 2 and 2. Break this down as 8 and 8. Break this down as 2 times 4. Break this down as 2 times 4. Break this down as 2 times 2. And we're left with a whole lot of 2's. A lot of 2's. How many 2's? 1, 2, 3, 4, 5, 6, 7, 8. 8 2's, 2 to the 8th power. Let me check that again. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is 2 to the 8th power. What's the point of breaking this down? Factoring it as we're going to do. When you factor it, you can see how many of what you got at the top and the bottom, and then we can do some cool canceling. 2 to the 4th power gets gobbled up, and this becomes 2 to the 4th at the bottom. You see what we did there? There's 4 2's up here, 8 2's down here, canceled out all the 2's that match to the top and bottom. So I'm left with 4 2's at the bottom, or 2 to the 4th at the bottom, and 3 squared at the top. So if I had to break this down, I would break it down in this way. That looks like a 24. Let me fix that, babies. All right, so I'd have this, and of course I can leave it as 9 over 16 as the reduction of this situation is a simplification. We're going to do the same thing here. We're going to simplify, but we're going to factor, and then we're going to see if we can cancel stuff out. So how do we factor this? We first look for a GCF. There is none. Then we see if we got to factor it in the form of the binomials, because this is not a perfect square trinomial, not a perfect square here, not a perfect square here. So what does the binomials tell me? It tells me, oh, figure out what values we have here, what two numbers multiply to give me a -3, yet add up to give me a +2, and that will be like -1 and a +3. And so I feel confident that I factored the numerator correctly. I'm going to do the same thing with the denominator. I first look for a GCF. There is no GCF. There's no greatest common factor, nor is this a perfect square trinomial. I got to process through and factor. I'm choosing this guess and check method because it's really easy when the coefficient of the lead term of that x squared is 1. It's just easy to kind of figure out, okay, what two numbers multiply to give me 12. yet add up to 7x. And what comes to mind is 3 and 4. So I have a positive 3 and a positive 4. So I have factored the numerator and I have factored the denominator completely. And so now that I've done that, I've got an equivalent situation here. Now what I'm going to do is see if there's anything I can cancel out, like the same 2's at the top and bottom. I'm going to cancel out the same factor at the top and bottom, that x plus 3 rather. And what I'm left with is the simplified version of this expression. It's going to be x minus 1 over x plus 4. And I'm done. So that is just a taste. I don't think I have any other examples. That's just a taste of where we're going to be going with simplifying expressions of this type and factoring. I look forward to talking to you soon. Thank you for letting me have another 11 minutes of your time for that lesson. I think it was worth it. If you got to fast forward, do what you got to do. But listen, I look forward to seeing you and talking to you soon. Be blessed. Bye-bye, baby.